Let's see how some of these shifting and exponential Laplace transform rules work out when we look at an example. So let's suppose we have an unforced resistor, inductor, capacitor circuit with these component values. So there actually isn't a resistor, so zero resistance. The inductor is 1 Henry, which is pretty big, and the capacitor is 1 farad, which is quite big. I picked these values, of course, just to make the numbers kind of nice. But suppose that this starts out, so the capacitor has 0 charge to begin with, but the current in the circuit is initially 1. So I guess 1, that would be 1 amp, which is kind of large current as well. Additionally, suppose that at time 10, so time 10 seconds, a switch switches the circuit to connect it to a voltage of 2 volts. So let's find the resulting charge function on the capacitor. If we wanted to draw a picture of this circuit, I guess we would need, so we'd have an inductor and a capacitor, oops, like this. But then there's a switch, right? The switch like this. And one part of the switch, the part that's initially connected, just closes this circuit. But the other part of the switch has a voltage source on it, so a battery or something. So at time 10 seconds, right, initially it's connected up in a freely oscillating loop, and so we'll get some sort of oscillation. But at time 10 seconds, we flip this switch to the other side, which connects it to this voltage. So at time 10 seconds, something different is going to happen with the behavior of this system. And let's see how that manifests itself when we do our usual solving the differential equation trick using Laplace transforms. So first, I guess we need to write the differential equation. So since our inductance is 1, we have 1 times q double prime plus our resistance is 0, so 0 times q prime. Our capacitor is 1, so 1 over 1 times q equals. Now we need to write the forcing, and write the force in a circuit situation. The forcing function is the external voltage, and that starts at 0 when t is less than 10, but when t is bigger than equal to 10, we're applying this external voltage of 2 volts. So we have this piecewise function as our forcing function. So to take the Laplace transform of this, we need to express this piecewise function using step functions. So just to rewrite this equation, we get q double prime plus q equals 2 times u of t minus 10. So this step function here, it's 0 until the step function turns on, at which point it becomes 2. So that is capturing this piecewise forcing function. So now we can play our usual game of taking the Laplace transform of everything in sight. So we need Laplace transform of q double prime plus Laplace transform of q equals Laplace transform 2 times the Laplace transform of u of t minus 10. Okay, so Laplace transform of q, that's s squared, Laplace transform of q double prime is s squared times Laplace transform of q minus s times q of 0 minus q prime of 0. And q of 0, that's an initial condition, and we said that the initial charge was 0, and also we said the initial current was 1, so we can put our initial conditions in there, plus Laplace transform of q equals 2 times, now Laplace transform of u of t minus 10, this is a shifted function multiplied by a step. The shifted function in this case is just the constant function 1. So a shift multiplied by a step turns into an exponential in the s world. So this is e to the minus 10s times the Laplace transform of 1. Okay, now on the left-hand side, we can gather up the terms that have the Laplace transform. So s squared plus 1 times the Laplace transform of q. Let's move this constant term to the right-hand side. So now on the right-hand side, we have a 1 plus 2 times e to the minus 10s times the Laplace transform of 1, which is 1 over s. So this term has an over s in it. All right, now that we have an equation with the Laplace transform, just solve for the Laplace transform. So Laplace transform of q is 1 over s squared plus 1 plus 2, actually I'm going to move these out front, 2 times e to the minus 10s times 1 over s times s squared plus 1. Okay, now think about taking an inverse Laplace transform here. This first term, we recognize that one. That's going to give us a sign, so this one's no problem. But the second term, to take the inverse transform of this, we're going to need to do partial fractions to make this denominator simpler. So let's work out partial fractions on this term before we go any further. So we have 1 over s times s squared plus 1 is going to be something over s plus bs plus c over s squared plus 1. All right, now we can clear denominators. We get 1 equals a times s squared plus 1 plus bs plus c times s. Okay, now we can multiply everything on the right-hand side out. For our squareds, we have an a squared and a b squared. So that times s squared. Left-hand side is 1. For our s terms, it's just c, so c times s. And then for our constant terms, it looks like just a. So looking at constant terms, we know that a has to be 1. Looking at s terms, we see that c has to be 0. And then looking at s squared terms, we see that a plus b has to be 0, but a is 1. And so b must be minus 1. So now a plus b is 0. Okay, so that means that our partial fractions decomposition is 1 over s plus negative s over s squared plus 1. Yes, okay. All right, so now we can come back to our Laplace transform here. So Laplace transform of q is 1 over s squared plus 1 plus 2 times e to the minus 10s times this partial fractions decomposition that we just found. So 1 over s minus s over s squared plus 1. Okay, and now we need to take inverse Laplace transform. Okay, so we get q on the left. On the right, we get the inverse Laplace transform of 1 over s squared plus 1 plus 2 times the inverse transform of e to the minus 10s times 1 over s minus s over s squared plus 1. Okay, now this first inverse transform, as we noticed earlier, this one is straightforward. We know this one. It's sine of t plus 2 times, but the second inverse transform is going to require a little work. So first of all, there's a multiplication by an exponential in the s world, and that means that in the t world, we're going to get a shift. So we're going to have to replace t with t minus 10 and a step u of t minus 10. This kind of makes sense because with this shift and step, this means that we're going to start the behavior, the charge function is going to start out looking like sine, but then at time t, something new happens, which is, what we expected to have happen because that's when we flip the switch. Okay, but the remaining part to take the inverse transform of is 1 over s minus s over s squared plus 1. So this is sine of t plus 2 times, so inverse transform of 1 over s is 1 minus inverse transform of s over s squared plus 1 is cosine t. Okay, and then we have to remember to do our shift, replace t with t minus 10, and our step u of t minus 10. Okay, so finally, our charge function is sine of t plus 2 times 1 minus cosine of, and here we do our replacement for t, cosine of t minus 10 times u of t minus 10. Okay, so there it is. Of course, it would be nice to look at a graph of this to see what actually happens to this system as time goes on. So let's graph this thing. So I have GeoGebra set up so that the Heaviside function is already here. So our function q of t is sine of t plus 2 times 1 minus cosine of t minus 10. And then the second term gets multiplied by u of t minus 10. Okay, so there it is. Initially, the system is just oscillating, right? That's no surprise because with a capacitor and an inductor, you just get a sinusoidal oscillation. But then right at t equals 10, that's when we flip the switch and the function all of a sudden changes somehow. Since the voltage that we're turning on is the constant voltage 2, essentially what happens is the charge on the capacitor starts oscillating around 2 because the capacitance is 1. A voltage of 2 is going to give you a charge of 2 as well. So it starts oscillating around 2 instead of around 0. And all of that behavior is captured by or calculated by the Laplace transform without explicitly having to work out exactly what happens at this discontinuity at t equals 10. So this is where the Laplace transform really starts paying off, because it lets us handle these discontinuous situations in a really elegant way without sort of treating them with any sort of special handling at all. We still just throw everything into the Laplace transform, solve for the Laplace transform, and then find an inverse Laplace transform, and the correct behavior pops out all on its own.